Hi, good morning. It's my pleasure to introduce our first speaker, our keynote speaker, Dayan. So Neve is an assistant professor at the University of Toronto in Canada. And his research is on the design and analysis of data structures for database and storage systems. Before he joined the U of T, University of Toronto, he worked for Pleops, a company here, and he was a technical advisor to SpeedDB. He received his PhD from the IT University in Copenhagen and was a postdoc researcher at Harvard. So please join me in welcoming Neve.
Shalom lekulam. Thanks very much for having me. I'm really excited to be here. There is a chance that because of my excitement, I'll talk too fast. If I do that, tell me to slow down. Okay, I'm going to talk about some research highlights from research we've done on data structures for storage systems from the past 10 years. I don't really come from the AI world. I come from storage, but I'll also try to cover some AI applications for this research to make it more relevant for this kind of context. Okay, so the talk is called Scaling Storage Engines for the AI Era. But let's start basic. What is actually a storage engine? I don't really have to say it for this crowd, but a storage engine is that component of a database system that structures data on a storage device, right? So if the if a user interacts with a database using a query language like SQL, the database will convert these queries into read and write requests of key value pairs to the storage engine, right? And the storage engine will convert these into blocked reads and writes to write on storage. Right, and these storage engines are at the heart of so many modern applications, right? And they control and impact the performance of, banking, retail, social media, and today, increasingly, many AI applications. So it's really not an understatement to say that storage engines facilitate the world's economy, and it's therefore important to get them to run as efficiently as we possibly can. Okay, so the core data structure that was used by these storage engines, maybe since the 70s, was the B tree. This is a data structure that probably everybody here knows from, undergrad. This data structure is a tree where every node in the tree corresponds to the size of a disk page, right? It imposes a sorted order over the data that you're trying to organize. And what's the problem with this data structure? Problem is, as updates come in, right, they trickle down the tree, they go to their corresponding nodes, but this ultimately leads to random writes on our underlying storage device. And why are random writes bad, especially random writes to small entries? Well, on a disk drive, this leads to mechanical latency, which is going to mess up your performance. On an SSD, right, the reason is similar. SSDs are composed of these 4 kilobyte pages. If you want to update a small entry on a disk page, or on an SSD page, right? Well, you have to read that page, write that page back. But if what you wanted to change is only a small key value entry, you've done a lot of work for no good reason, right? So ideally, you want to, process a lot of entries within the page that you're reading. Okay, so this question of whether random writes could be eliminated from storage engines is a question that started being asked in the database community in the 90s. And one of the best data structures that came up as a replacement for B trees to handle this problem is the log structured merge tree. So this was invented in 1996 by Patrick O'Neill at the University of Massachusetts, along with some colleagues. And the way that this structure works is it basically just buffers everything that you want to modify, right? It batches insertions, updates, and deletes in memory. And when that buffer fills up, you flush it to storage as a sorted file. And then later on, you just sort merge these files. Okay, so what does that mean? That means that you never actually issue any random writes to your storage drive. You only ever issue large sequential writes. That's going to be a much more friendly I/O pattern on modern storage devices, right? On both disks and SSDs. Okay, so that's good. I'm still at a high level. I'm going to talk about some applications now, and then I'll get back to the core, to the inner guts of LSM-trees. So these LSM trees are really used right across a wide number of applications. If you've heard of key value stores like RocksDB, Cassandra, and HBase, they all have an LSM tree running at their core. If perhaps you've heard of relational databases like MyRocks, CockroachDB, or YogaBytes, so these are actually relational databases, right, with tables and indices and everything. But behind the scene, there's actually an LSM tree that organizes all of that relational data and storage. Right, so that's increasingly a common architecture as well. Something I perhaps want to pay more attention to in this context is vector databases and RAG pipelines. So LSM trees are increasingly used in this context, and this is more of an AI kind of world. So let's talk about this. So vector databases, what are they actually used for? Well, the main application of vector databases, the main problem they allow you to solve is to compare and do similarity search across complex objects, like images, like videos, like perhaps sound bites. So how does a vector database do this? Well, it takes these complex objects and it uses this magical piece of software called an embedding model, right? And it passes them through the embedding model, and the embedding model basically takes these images or complex objects and embeds them in a high-dimensional space such that similar objects are actually close to each other in that high-dimensional space. Right? What you can then do is construct a graph on these high-dimensional points. We call these high-dimensional points vectors. And then you can basically navigate the graph. So given a query, right, you start somewhere in the graph, and you navigate the graph towards the nearest neighbors in the high-dimensional space. And that allows you to find similar objects. Okay, so the way that a lot of these modern, vector databases work, like Milvus, Weaviate, Pinecone, is you actually have two components in the system. You have this graph index that I just talked about that allows you to do similarity search. But then you also have some other index, typically structured as an LSM tree, that allows you to do exact search. So what would a query here look like? Suppose you want to say, I want to find movies that are similar to The Godfather, but I specifically want them to be, maybe from 1983. So I'll start by doing a k-nearest neighbor search on the graph. The graph might return some similar movies, right? In this case, Goodfellas and Scarface, some other gangster old movie films. I'll then take that and I'll go to the LSM tree to do the exact search over the year, right? Because the year is an exact attribute. And then, right, from the LSM, I'll know, okay, Goodfellas doesn't count, it's from the wrong year, but Scarface actually does count, right? So this allows me to complement, right, to do similarity search plus exact search. And, And these software components are actually used behind the scene for LLMs. All right, so today, and this is what's known as a RAG pipeline. So RAG stands for Retrieval Augmented Generation. So how does this work? And I'm really providing a very, very simplistic impression of this, just so that I can prove to you that LSM trees are actually used in this context. Users will interact with an LSM by issuing prompts. Right, the LLM, large language model, will then find relevant knowledge bases that could be used to answer, the prompt issued by the user. It will perform an approximate nearest neighbor search on these graphs, like I talked about just before. We might refine whatever, the graph returns using an exact search over an LSM, right? And that will allow us to return better, hopefully high-quality results to the user. Okay, so hopefully, right, this is all to say, right, that this data structure that I'm going to talk about is actually the backbone of many important modern AI applications. And as such, right, we want it to run as efficiently as possible. So now I'm going to get back to the actual data structure, and I'll try to talk about three things in what comes next. How does it actually work? I'll probably spend about 5 minutes there. How does it scale as the data size grows specifically? And then third, what can we do to improve it? And there I'll talk about some research project from my lab over the past 10 years. And I'm just realizing my water bottle is over there, so I'm just going to grab it. Any questions so far? Questions, complaints? Okay, good. The edges are, so the edges are actually artificial, right? So the nodes are these vectors. The edges you actually construct, the way you actually do it is you try to make sure that every node has some edges that lead to far away vectors and some edges that lead to close by vectors. It's a heuristic thing. Yes, it's constructed by a certain distance with some long edges so you can take shortcuts, and then you can kind of narrow down to the closest node like that. Good question, thanks. Okay. So how does an LSM tree actually work? Okay, well, there's a buffer in memory, and that buffer ingests key value pairs inserted by the application. Right, so these are just keys and values, right? Nothing fancy. Whenever the buffer fills up, we sort it and flush the result as a file into storage, right? So we call that a run, and this is just a sorted array of key value pairs. Now we can continue doing this, and we can continue gathering these sorted runs in storage, but that's not going to be so good. That's going to mess up our read performance, right? If we're searching for something, we'll then have to search all of these. So instead, what we're going to do is to sort merge them, right? And how does that work? That just takes a linear pass over the key value pairs in the files, and just sorting them, merge sorting them on the new file. Okay, now because we always take files that are of similar sizes and merge them into something that is like twice as big, these files follow, these files are exponentially increasing in sizes. Okay, and so the LSM tree organizes them as these levels, right, of exponentially increasing capacities. All right. How does an update work? So all updates actually work out of place. That means even if there is an old version of an entry here, if we want to update it, we write a new version of the entry into the buffer, right? Eventually that entry gets flushed, right? So the newer version coexists with all the older versions. That also means that in order to make a search and find the most recent version of an entry, we have to search the LSM tree from smaller to larger levels. That also corresponds to younger to older data. Okay, and that allows us to find the most recent version of an entry. Later on, when we do compaction, when we merge files, that allows us to identify older versions of entries and actually get rid of them. So that's our garbage collection mechanism. Okay, how do we search this thing during a query? Well, the simplest thing that we can do is we can do a binary search across each one of these files because they're sorted. But that's actually going to be kind of slow because that's going to involve a lot of hops in storage, a lot of I/O. We don't want to do that. What typical systems do is they'll store an index. I mean, I call that fence pointers. And basically what it does is it stores the first key of every storage page of every one of these runs. So that means you can basically do a binary search here to find the relevant page that contains the key range that you're trying to access. And using those, you can access, the correct page with just one I/O for each one of these. In addition to these fence pointers, there are filters, typically Bloom filters, that also allow so you have a filter for each one of these runs. And you can access the filter before to allow you to skip accessing the relevant run, right? So a filter is a probabilistic data structure that allows you to answer set membership queries, and it can tell you if a key for sure doesn't exist. I'll talk more about those later on. Okay, let's talk about scalability. So because these levels of the LSM tree are increasing at an exponential rate, this means that the overall number of levels is log of n, right? Where n is the data size. And this R corresponds to the fan out of the tree, the size ratio between these levels. Okay. That in turn implies, right, I'm still at a high level, that implies that your read cost and your write cost are both going to scale as log of n with respect to the data size. Why? Because as you have more levels, your reads have to search more levels, right? But also every entry is getting merged across a larger number of levels. So the overhead for writes also increases at a logarithmic rate. So the question that we're kind of trying to ask in this presentation is, to what extent can LSM-tree handle exponential data growth given how it scales? And well, we just saw it scales in a logarithmic rate with respect to data size. Now, if your data size is growing at an exponential rate, and you take an exponential function and feed that into a logarithmic function, it's not that great, right? Then basically your performance is scaling linearly as time goes by, and that begs the question: can we do better, right? So can we take LSM trees and actually scale them as a slower function with respect to data growth? And that's what we'll try to do. Okay, so I'm going to present 3 different papers that we have from the past 10 years. 2 of them are actually a little bit old, from 2017 and 2018, but one of them is very, very new. These are a few of my best works. This first one was, among the 4 top papers in SIGMOD 17. The second one is among the 10 best cited papers in SIGMOD 18. And actually, the last one that I'll talk about just got a Best Paper Award for VLDB 2025, right? So these are decent papers that, will hopefully be worth your time. Okay. Any questions so far? Other questions? Yes. So that's correct. I mean, a read. So what's the question? Okay. So you know what? Let me defer that question for when I talk about this paper here, because then when I talk about the second paper, I'll actually provide a total cost breakdown of write cost, and then we'll get back to this. But thanks for the question. Yeah. Yeah, that's a great question. So SSD write amplification and garbage collection will actually make all of these overheads worse. Okay, so there's a conventional wisdom that says that LSM trees should not lead to too much SSD write amplification. And the reason for that is that they're performing these large sequential writes, and data that you're writing at the same time also dies at the same time, which this should in theory be friendly for SSDs. The reality is more complex. The reality is, if you have multiple streams that are writing at the same time, data might get interspersed in the SSD. That could actually lead to a lot of garbage collection. So LSM trees are subject to that problem as well. It's going to make things worse. We actually have a paper that I'm not talking about today about how to manage this. The paper is called Spooky from VLDB 2022. That's the paper that I did in collaboration with Plyops, actually. Eddie's a co-author, and he's over there. I'll be happy to talk to you more about that offline, perhaps. But basically, yes, you're absolutely right. But these are orthogonal overheads, right? And if we improve one of them, the total overhead will still go down. So, yeah. Okay. So let's get going with the first paper. So this paper is called, and how am I doing with time, by the way? I don't see a clock, can I? 27, okay, cool. Okay, so let's get going with Monkey. So Monkey stands for Optimal Navigable Key Value Store. And what we try to do with this paper is to take the filters and figure out how to allocate memory optimally across these filters of the LSM tree. Okay, so just briefly, what is a filter? So a filter is this probabilistic data structure that allows you to test whether a given entry exists in a set. So, you can ask, does a given key exist? And the filter can return either a true positive if the key does exist, or if the key doesn't exist, it can return it will return a false positive with a probability of epsilon, or a true negative with a probability of 1 minus epsilon. Okay, and in this way, filters allow, they basically are a lossily compressed representation of the data, so we can store that at a higher level of the memory hierarchy, and by so doing, they allow us to save accessing storage. Okay, and the most classic and widely used kind of filter is the Bloom filter, and here's how it works. So it's just a bit vector with k hash functions. To insert a key into this thing, you hash it using the k hash functions, mapping them to k random bits. And for each one of those bits, you set it from 0 to a 1, or you keep that bit set to 1 if it's already a 1. So in order to query this thing, right, again, you take a key, hash it using the k hash functions into random bits. If at least one of the bits is set to 0, you know the key for sure doesn't exist, right? Because otherwise that bit would have been a 1. But if both bits, or if all k bits are 1s, then either it's a true positive, or it could be a false positive because other keys happen to set those bits to 1s. So that's how that works. Okay, so in the context of LSM, again, we have one of these Bloom filters for each one of the runs in storage. And a read will, before it goes to storage for a given run, it will check the filter, and the filter might return a negative. This is excellent for us. It allows us to skip a storage access. It might return a false positive. This is bad. This is what we want to try to avoid, because this is a storage access that goes to storage and doesn't actually find what we're looking for, so it doesn't do any useful work. Or we can get a true positive, in which case we actually just go to storage, find what we're looking for, and the read terminates. Okay, so we observed that all systems using this in practice assign the same memory footprint to all of their filters. So, right, so we describe this memory overhead in terms of bits per entry, right? So there are m bits per entry for each one of these filters. This in turn means that each one of these Bloom filters is proportional to the size of the run in storage that it corresponds to. Now, with respect to the number of bits per entry, right, the false positive rate for a filter is something like 2 to the power of minus m, where m is a number of bits per entry. It's a bit more complex than that. I'm simplifying things, but let that be the false positive rate for now. Now, with respect to the false positive rates across all the different levels, what you can do is reason about the worst case number of storage accesses that on average don't do any useful work for your query. And that just turns out to be the sum of the false positive rates across all the filters. Right? That's the average number of IOs that don't do any useful work. And what we showed is that it turns out this is not the best upper bound that you can achieve with a given memory footprint of m bits per entry. Right? So why is it this, by the way? It's this because this is a false positive rate for a single filter, and you just multiply that by the number of levels in the tree, which is log of n. But it turns out you can do better than this. So why is it that you can do better than this? Well, I said already that these filters, the size of each one of them is proportional to the run in storage that it corresponds to. That in turn means that the largest filter in the system contains most of the memory in the system, but that filter is actually saving you only a small fraction of the overall amount of work that a read has to do. Right? It saves you 1 IO. Right? So that's a reason to be suspicious. Most of the main memory is only saving us a small fraction of the overall amount of work we have to do. Right? So the core insight is let's be a bit cleverer about how we allocate memory across these filters. So let's take a little bit of memory, maybe from the largest filter, and reallocate that to smaller filters. Right? Because smaller filters contain exponentially less data, this is actually going to allow us to set, right, kind of linearly more bits per entry to filters at smaller levels. And that, right, and okay, so that will cause an increase in the false positive rate at the largest level, but actually because smaller levels contain exponentially less data, the decrease that this is going to cause to the false positive rates at smaller levels is more than going to offset the increase at the largest level. Question? It's a good question. So here I'm assuming that. So yes, the largest level is the largest one. I'm assuming that you have that block index in memory that allows you to access each one of these levels with just 1 IO. Right, so there's an assumption here that because you can actually store the block index in memory, the cost for accessing each one of the runs is the same regardless of their size. In reality, what you're saying could be correct if you don't have enough memory to actually store that block index. Then the cost there will be more expensive. in that case, this is still a good idea, but there are some nuances to how the analysis plays out. But it's a good question, great question. Okay. Okay, so what does this allow you to do in terms of guarantees? Well, the core observation is that now, right, the false positive rate, this causes the false positive rates to actually decrease exponentially across smaller levels. That means that now the sum of the false positive rates across the levels becomes basically a geometric series that converges with respect to the number of elements in the series. Right? So that allows you to basically shave a log of n factor from the overall query cost. And that allows you to scale queries better. So we implemented this on top of RocksDB. Right? And here, this is an experiment where we increase the data size on the x-axis, we measure query latency on the y-axis. And right, we see that, you know, with this paper monkey, performance stays stable, while with the default RocksDB, performance, right, latency goes up because as the data size grows and as you have more levels, there are just more false positives that take place. So more storage accesses take place. Okay, that's the first key, and that's the key to scaling point rates. And that's the first paper. Any other questions? Yeah, I'm actually becoming conscious of time, so let me get going with the second one. So the second one is called Dostoevsky. It's from 2008. It stands for Space-Time Optimized Evolvable Scalable Key Value Stores. I apologize. Okay, so in this paper, we tackle the problem of write amplification in SSDs. And here I come back to your question. So first of all, let's try to reason about write amplification, like write cost. So what is write amplification? Write amplification is the number of times that an entry that the application writes actually gets merged in the LSM tree. So it's the overhead that we actually pay. So let's reason about how many times a given entry gets merged across the LSM tree. Okay, so to do that, let's first of all start with reasoning about a single level. So the level is empty. Some entries are written onto it. Let's suppose that there is an entry here. It was just written, so it was written once. Then it participates in a bunch of merge operations. And right, the core point is that after our merge operations have taken place, where R is basically the fan out of the tree, at that point, this level is full, and we take everything here and flush that onwards. Okay, so the point I'm trying to make is each entry is getting merged R times per level, where R is the fan out of the tree. And you can now take that and sum that across all the levels to get your overall write amplification. All right, so this is the overall number of times that each entry gets merged from the time that it's written the first time until it gets to the largest level. Does that kind of answer your question from before? So this is, okay. So now I'm going to optimize this cost, but okay. So let's do that, and then if there's still a question, you can let me know. Okay, so that's our analysis for write costs. So that's good. However, recall now from the last paper that I introduced that the optimal way to assign false positives to our Bloom filters was actually to set them exponentially decreasing false positive rates for smaller levels, right? So what does that mean in this context? Well, what it basically means is most of my read overhead actually comes from the largest level because the false positive rate for the Bloom filter there is exponentially higher than the rest. But on the other hand, there's an asymmetry here because my write cost is derived equally from across all the levels, right? So most of my read cost is coming from the largest level, whereas my write cost is coming equally from across all the levels. That implies that all of this work that I'm doing for merge sorting entries at smaller levels is in some way a little bit redundant. Right, at smaller levels, this is where I'm doing most of the work, but most of that work is not actually that useful towards curbing and reducing my point read cost. So what do we propose to do to solve this? Well, basically, we propose to make compaction at smaller levels lazier, less proactive. What's going to save us with respect to read cost is exactly the filters and the fact that at smaller levels, they have smaller false positive rates. We'll have more runs at smaller levels, but their false positive rates for their filters will be lower, and that's going to make up for the fact that there's more of them. So our queries will stay fast. That's the promise. Okay, so I mean, that's basically the design. So in this design, we do lazy merging across all the smaller levels and eager merging only at the largest level. What does that mean? for each one of the smaller levels, we make a compaction only when the level fills up, right? So you can gather multiple overlapping sorted runs only when the level fills up. You merge it into one sorted run at the next larger level, right? On the other hand, whenever new data comes into the largest level, you make a compaction immediately. Okay, so there's only one sorted component at the largest level, multiple sorted components at smaller levels. Okay, so let's reason about the performance that this allows us to achieve. So in terms of optimizing write memory across the Bloom filters, it's similar to what you saw before. It still pays off to set exponentially decreasing false positive rates to Bloom filters at smaller levels, right, to optimize the overall read cost. But in terms of writes, this is where we get our win. Now every entry is getting merged one time per level across each one of the smaller levels. But still, at the largest level, we're still paying a higher price as before. The point is that now our write cost is, our write amplification is becoming R plus log of n, and this is better than the R times log of n that we had before. Right, so we get a win. We get a win in terms of write cost without significantly increasing our point read cost. In the subsequent year, we had another paper that actually showed how to push this even further and get from this cost to a log n cost. I'm not going to talk about that in any detail. Right, but here are some performance figures that kind of show you the impact in a tangible way. Here again, we're increasing the data size exponentially on the x-axis. We're measuring write latency, and we see that these two new designs win in terms of average write latency. But what's cool is that at the same time, they also win in terms of read latency, right? So and the reason that read latency doesn't get harmed is because of the Bloom filter optimization, right? The filters at smaller levels still have lower false positives, so they allow us to skip most of the runs, even though we have a greater number of runs overall, right? So the lesson is you have to co-design the filters and the compaction policy at the same time. Okay. So that was the second paper. Any questions about this? Okay, how am I doing with time? 41? Okay, so I think that's good. So one more paper to go, and this is actually the one that I'm most excited about because it's very recent, and actually my student presented this last week at VLDB. So this is called Diva. It just got the Best Paper Award for VLDB. It stands for Dynamic Range Filter for var-length keys and queries. The mastermind for this work is actually Naveed, who is my PhD student, and we also collaborated on this with Joanna Bercea from KTH. Okay, so what's the context? What's the motivation for this work? Okay, so I'm talking a lot about filters in this presentation. Again, this is also about filters. Recall that for a point query, right? You have these Bloom filters. They ideally return negatives, and they allow us to avoid skipping runs in storage. But what if you have a range query, right? So suppose that the application is trying to query for all keys between 5 and 8, right? And the question is, can we use filters to actually improve this kind of query? So you might think, can I use a Bloom filter for this? And the answer is partly, but it's not that great. So, one thing that you can do is take basically every element that exists within the range, you can check whether it exists in your Bloom filter, right? But this means that you have to issue R queries to the filter where R is the size of your range. So that's going to be pretty slow. But also, this is going to mess up your false positive rate, because as soon as you have one false positive within that range, there might be at least one key, and then you have to go to storage, right? And our goal is to avoid accessing storage for these range query if the range is actually empty. The other limitation here is that this simple approach that I just mentioned only works if you have integer data, right? So if you have strings, you can have infinitely many keys within a given key range. And in that case, this approach just doesn't work. You can't issue infinite queries. Okay, so here are our goals. We want to design a range filter to also allow range queries to avoid accessing storage when the range is empty. And we want to do so while ensuring that we have fast queries, a false positive rate that is on par with that of Bloom filters, with respect to a given memory budget. We want to support And on top of this, we want to support variable length keys, right? Keys of any length, strings, basically. And we want to support variable length queries, so queries of any length, right? So if the range is small or if the range is large, it should cost the same, and it should return a negative if there's nothing in that range. So these are our goals. It turns out that there's actually a lot of work on this problem from the past 10 years. We're not the first ones to address this problem, but we're the first ones to provide a solution that's adequate across all of these goals at the same time. Okay, so here's what we propose to do. What we propose to do is to store the keys in a sorted order. So there's no hashing in this. We're actually storing the keys right in a lexicographical order. What does that allow us to do? This allows, so if you have a query, here is how we actually check for whether a range is empty or not. We check for the successor of the starting point of the query. And if the successor is greater or smaller than the ending point of the query, that tells us if the range is empty or not. Okay, so this is the main thing that will allow us to check if the range is empty or not. So basically, now what we need to do is to propose a data structure that allows you to do fast successor search over compressed keys while keeping these keys in lexicographic order. And if we succeed in doing that, then we have a range filter that actually allows you to work like this. So how do we do this? So first of all, we think about the keys as existing along this cumulative distribution function. So what we're now going to do is we're going to sample every 1,000th key. And right, and we note that these keys, these samples that we pick, actually allow us to approximate the distribution. Right, so we're kind of assuming here, but this actually works for many data distributions, that the 1,000 keys in between any two of these samples are approximately uniformly distributed, right? Because the samples kind of approximate most of the distribution. And this is a point that we're actually going to use, this assumption that keys in between the two samples are uniformly distributed. What we're now going to do is build a tree from the small fraction of samples that we've taken. So this is a small tree that takes up about 0.1% of the data size, right? Because it's only built on very few samples. So typically this tree is actually going to be in your CPU caches. This is pretty fast to query. The question that remains is how to organize the 1,000 keys in between two samples. Right, so sorry, I guess I'm hurrying up a little bit because the end of the presentation is near, but still. So how do we organize the 1,000 keys in between two samples? Well, we use this data structure for them called an infix store. And this is basically an order-preserving hash table of compressed keys. So how does it work? Well, okay, so here are the 1,000 keys in between two samples. Here's how we're going to process them. The first thing we're going to do is remove the greatest common prefix. Why? Because this information is redundant. It's the same for all of them. We may as well get rid of it. It can be inferred. So we're not actually losing any information by getting rid of it. The second thing we're going to do is remove a suffix from all the keys in order to homogenize their lengths. And this is actually where we do lose some information. And this is where our kind of lossy compression comes in. What's left are a bunch of infixes, right? So an infix is just a string of bits in the middle of all the keys, right? And these infixes, because they're near each other and because we've removed the greatest common prefix, they're sort of uniformly distributed, right? Because so these are the bits that actually kind of allow you to differentiate between a bunch of keys that are near each other. So this is, okay. So how do we continue? For each one of these infixes, we're going to further divide it into an address and a fingerprint. And we will then, so the address has, maybe about 10 bits of the overall infix, and the fingerprint part has as many bits as you need to guarantee a given false positive rate that you want, right? So this is basically your tuning parameter, the length of, this part of the infix. You then take these and store them in a very compact hash table. Right, and so basically, the address part of the infix is stored implicitly. That's just the address. The fingerprint is actually stored within that address. Right. So what does this give you? This gives you an order-preserving hash table with basically constant time access, assuming that these are actually uniformly distributed. And if you have, as long as you have kind of a smooth data distribution, these will be approximately uniformly distributed. If you have kind of jagged distributions, this will work less well. So I'm kind of saying that as a caveat. This works for many data distributions, but actually not for all data distributions. Okay, so here's how our overall data structure looks. Right, we have a cache tree in memory, and we have a bunch of infix stores as the leaf nodes. And so, okay, so how do we process a range query using the structure? Well, if this is a key space and here's a query, well, we just search the tree. If we find that one of the samples in the tree actually overlaps with your query, then we know for sure this is already a true positive. We can return a true to the user. The harder case is if the entire range is subsumed within one of the infix stores. In that case, we have to go into the infix store and query it internally. And again, here, if we see that there is one infix that's in between your range, right? Because this is in lexicographic order, then we can return a true positive. The way in which you get a false positive is if both the starting point and end point of the query match with some existing infixes that exist in your infix store. And if that happens, then you can't actually know if the range is empty or not. That's how you actually end up with false positives. But that happens with a probability that depends on the size of these fingerprints. And that happens with a probability of something like 2 to the power of minus m, where m is the number of bits per entry that you assign the data structure. Okay, so this is kind of a simplified view over how this works. But what this allows us to do is actually skip most of the runs in the LSM tree. So we replace the Bloom filters using this data structure. And now for a range query, we can also skip most of the runs that don't contain any relevant information. Right? And assuming that maybe there's only one key across the tree that qualifies under the range query, then this overhead goes from log n to constant. Okay, so we went here too. Yes. So they learn the CDF too, but they do it for a different purpose. What they're doing, so in Team Kraska's work, the goal is to not provide you with a filter, right? It's an exact index, and rather than incurring the log n cost of traversing the hierarchy of nodes to get to the target, the result, the idea is to have a bunch of linear regression models that kind of predict where to go and get there more quickly. So basically, in his work, you're trying to reduce the log of n cost for traditional index data structures. Here, I mean, admittedly, we're getting inspired by Tim Kraska's work. So we're getting inspired in the sense that we are learning the CDF, like to fit the data. But this is a filtered data structure. So it's a data structure with different semantics, right? This is a range filter, right? They did this for traditional indexing data structures. But there's definitely, right, these are cousin data structures. Okay. I'm almost at the end. So let me just kind of conclude, and then I'm not actually sure what my time is, but then we can do a Q&A at 10 minutes. Okay, that's good. Yeah. Yes. So, okay, yes. So there are stronger assumptions here. So this is actually worst case for any kind of workload. This is under a few assumptions, and let me clarify them. The first assumption is that your workload distribution is kind of smooth. So this will work for like a normal distribution, a Gaussian distribution. This will not work if you have a workload distribution that's like, it's extremely jumpy, right? Because then the performance for the, infix stores it's just not good. It's still going to work, but it's not going to perform as well. The other assumption, just behind the O of 1 cost here, is that most of the levels don't actually contain any relevant data for the range query. If every level actually contains some relevant data, then the filter doesn't help you. But thank you for the question. Okay, so we have some other work that I'm not talking about today, also in this area, right? So we have a VLDB 2022 paper that shows you how to optimize space, but also SSD write amplification, as per that question there before. We also have a Sigma 21 paper that shows you how to better optimize the CPU footprint of all your filters, but I'm not talking about that today. But anyways, I'm going back to the question that we asked at the beginning of the presentation. Can we take these LSM trees and can we scale them better for exponentially increasing data sizes, right? And the answer and basically the answer is yes, right? So there are various optimizations that we can do to make them scale better with respect to data size. Going back to AI applications, right? Given this data structure is the backbone of so many AI applications, right? The idea is that this can hopefully allow our AI applications to run faster too, with greater resource economy, and maybe that's one of our ultimate goals, right? To help users. We're also in the lab at the University of Toronto. We're working on putting all of these optimizations within one system that's a fork of RocksDB. We call it OrcaDB, and it's a work in progress, and we hope to open source it eventually. Probably not as a commercial product, but more as a research prototype that other researchers can take and use and build on top of to benefit from these optimizations. And I think that's all. So thank you very much. Yeah. Good point. So I didn't actually measure, so I didn't talk about tail latency at all in this talk. I think all the optimizations that you find here, though, will help you with tail latency, right? So, the Bloom filter optimization, right, means that you have fewer false positives. That also means you'll have a lower tail latency. The write optimization, right, cuts down the number of times you merge every entry, right? So there's going to be less compaction. So compaction is going to interfere with user operations less, right? So again, so I think that with most, it actually kind of depends on how you do it. There are a lot of subtleties. I mean, it's also about how you granulate these compaction operations, but we're basically still relative to, it depends on what you compare it to. If you compare it to something like RocksDB, right? RocksDB actually pays a lot of compaction costs at each level. So relative to that, the overall amount of work that we do is lower, right? And then it kind of comes to how you granulate these compaction operations to determine how much they're going to impact user operations. We talked about that in like some other paper actually, but I mean, yeah, it's a very good question, and I'm sorry that I'm kind of hand waving. Yeah. Yeah.
Can you touch on what's the difference between updates and new data that's being written? You have two use cases. One is putting new data all the time. The other one is constantly updating the same data. How does that affect performance?
Okay. So an insertion is an operation that will eventually reach the largest level. It's going to get merged the maximal number of times as it trickles down. So it's going to incur the maximal write cost. An update, on the other hand, might actually get compacted with the older version of the same entry before. So basically, in that sense, updates can be seen as cheaper, right? Because the older entry will get eliminated before, so it's like less times that you're merging an entry until it gets to the very end. In this work, we actually kind of assumed insertions for the whole time because we're kind of interested in measuring worst case guarantees. Updates will make costs cheaper for you, especially if you have like a skew in the workload. Yeah. I mean, actually, it's a great point because like we were concerned mostly about worst case overheads here. If you care about average cost overheads with respect to a given skew, then probably you want to fine tune these optimizations for the workload. Okay, so I don't see any other questions. So I'm happy to talk to people offline. Thanks again very much. I'm really excited to be here. Thank you.